By the way, I put up all of these lectures online, and Andre has sent some of these, I think, but you can find these all online if you would like to go back to the slides for some reason. And some longer versions of these lectures are online also. I don't know when I will get a chance to put these up, these recorded ones. Okay, we were looking at quality of service-aware memory systems. We talked about one approach, which is a smart resources approach. We were talking about quality of service-aware memory controllers. And I'll continue doing this, and we'll cover dumb resources a little bit, like source throttling, keeping the memory controllers, interconnects, and caches simple, but complicating some other part of the system, like source throttling, quality of service-aware data mapping to controllers. I won't talk about thread scheduling, but that's also interesting, I think. Let's continue. Last time we left off at Atlas memory controller, if you remember. And the idea was to have the memory controller keep track of the attain service of each thread at a long quantum, long interval, and prioritize the threads, rank the threads based on the attain service, where the threads that have attained the least service that are ranked the highest are prioritized. This was good for throughput. It had low complexity, and it eliminated the problem of coordination among controllers. In fact, because it was coarse-grained, if your mapping is nicely distributed across that coarse-grained interval, you may not need any coordination across controllers because of this. The downsides, some threads get delayed significantly with this, because some of them, there are many threads that have long memory episodes. As a result, these are memory-intensive threads, and they get delayed significantly, so we have high unfairness. We're going to try to solve that problem with this one, thread cluster memory scheduling. And I had briefly talked about this when I talked about asymmetry in multi-core architecture. So this is going to be an asymmetric scheduling algorithm. So the problem is, with these previous algorithms that I described to you, you get either high throughput or high fairness, not best at the same time. So this is empirical data based on simulation with 24 cores, 4 memory controllers, approximately 100 workloads. We plot the weighted speed up. I'm going to call the system throughput. You may disagree with it, but and I disagree with it sometimes also, but the metric is similar with harmonic speed up also. You get better as you go toward the right. And this is the fairness metric that I'm going to use, which is maximum slowdown. Basically, this is the slowdown of the thread that has been slowed down the most so far. This is not the perfect fairness metric, perhaps, but this actually bounds the fairness, and it takes into account performance a little bit. And I think Andre has a paper on that. Ideally, we would like to minimize this. We'd like to minimize the maximum slowdown and maximizing the weighted speed up. If we look at Atlas, it has a system throughput bias. You cannot see it here, but if you compare it to PAR-BS, parallelism or batch scheduling, this has more of a fairness bias. It's more fair, but it doesn't get the best throughput. Stall time fair memory scheduling is no good for anything, according to these two metrics. And first ready, first come, first serve, row hit first scheduling falls here. And first come, first serve, no scheduling at all falls here. And it got lucky in these workloads. I think it has reasonable fairness. So no previous scheduling algorithm provides the best throughput and fairness at the same time. We would like to reach toward this frontier. And let's take a look at why this is the case. If you look at the throughput biased approach, this is similar to Atlas. Basically, these approaches prioritize less memory intensive threads. These rank the threads according to their memory intensity somehow, attain service, and prioritize thread A. This is good for thread A because it can keep its core busy, compute, and it improves overall system throughput, overall core utilization. This is very bad for thread C because it starves, because there are many threads in front of it that get prioritized before that. If you look at a fairness biased approach, one way of providing fairness is have threads take turns accessing memory. Basically do round robin at some interval, at some grain. This is good for thread C because it doesn't starve, which is memory intensive. But this is bad for thread A because it doesn't get prioritized. As a result, you get reduced core utilization. Even though if you could prioritize this thread and it doesn't hurt anyone else, perhaps. And that's the observation. Basically, we observe that single policy for all threads is insufficient. So how do you achieve the best of both worlds? The basic idea is, for throughput, we would like to prioritize these memory non-intensive threads, because prioritizing these threads enables them to make progress, and it also hopefully doesn't hurt the performance of other threads. For fairness purposes, unfairness is actually caused by these memory-intensive threads being prioritized consistently over each other. Not because of these threads, these little mice being prioritized over the elephants, but the elephants being prioritized over each other consistently. As a result, we're not going to allow that. We're going to shuffle the thread ranking among the threads that are intensive for fairness purposes. And it turns out some of these threads have high vulnerability to interference. Some of these threads have low vulnerability to interference. Remember the random access versus streaming example. Even if they are the same intensity, random access thread is more likely to get slowed down because streaming thread keeps a bank hogged for a long time. So we're going to take into account the different vulnerability to interference. So this shuffling will be asymmetric. Shuffling meaning some thread becomes the highest thread for a while, and that thread gets shuffled over time. So that's the idea, basically, with thread cluster memory scheduling. The scheduler groups threads into two clusters. Among all the threads in the system, some of them are memory non-intensive, some of them are memory intensive, and two clusters are formed with these threads. And the non-intensive cluster is prioritized over the other one to maximize throughput. And there are different policies for each cluster. Within the non-intensive cluster, we rank the threads and prioritize them based on their intensity for throughput again. Within the intensive cluster, to achieve fairness, we shuffle the thread ranking. So let's take a look at how we cluster the threads. Basically, first we sort the threads based on their intensity. Misses per kilo instruction is one measure of intensity. And we calculate the total memory bandwidth usage at the memory controller for these threads. That's the attained service of all threads, if you will. And non-intensive cluster is formed by those threads that have a fraction of that memory bandwidth usage. And that's alpha times that memory bandwidth usage. In this case, we set alpha to 10%. It could be less than that, and we're going to vary that and see that it has an effect on both fairness and performance. So these threads that consume a little fraction of the memory bandwidth are deemed to be non-intensive, and everything else is deemed to be intensive. That's how you divide the clusters. Yes?
Memory bandwidth depends on, it does not depend on the misses per kilo instruction. You also have the performance.
Memory bandwidth is affected by how many misses that you generate,
yeah.
right?
But not per kilo instruction.
That's right, yes. Yes.
So what is alpha exactly?
So this part, this T memory bandwidth is actually memory bandwidth. This is data rate.
Okay. So
and alpha is...
And how do you compute alpha?
So let's say over time, alpha is a parameter. So over time, over an interval, you figure out what's the total usage.
What's the total usage and what? And you, okay.
Yeah.
So then you can attribute.
Exactly. You can attribute the alpha. But the threads are sorted based on MPKI. Okay? Okay. So the non-intensive cluster is prioritized over the intensive cluster. This increases system throughput, and we've already discussed that. And this doesn't degrade fairness. Unless you make mistakes, of course. Unless you cluster a big thread over here. And that does happen, because whenever you have a single threshold, you make mistakes in some workloads. Okay. Okay. Within the non-intensive cluster, actually, the policy is simple. Basically, we rank the threads based on their MPKI. And the lowest MPKI thread is prioritized over others. Again, the purpose is to maximize throughput. Again, actually, this doesn't matter. This policy doesn't matter if these threads are actually light. Unless you make mistakes in clustering, this policy doesn't matter. Intensive cluster is the more interesting one. Basically, the memory controller periodically shuffles the priority of the threads. Basically, the most prioritized thread changes with fine-grained intervals. And this increases fairness, but treating all threads equally is not good enough, as I discussed earlier. Some threads are more vulnerable to interference, because equal turns doesn't mean same slowdown, because threads have different vulnerability to interference. So let's take a look at why this is the case. Actually, we discussed this earlier in some other context. So we did this experiment where you have two intensive threads contending. One is random access and the other is streaming. Remember these benchmarks that we ran on real systems. We did the simulation study also. So if you actually prioritize the random access thread assuming these are equal memory intensity, if you prioritize the random access thread, streaming thread slows down by about 7x. And this is a very heavily contended system. We wanted to simulate that. If you prioritize the streaming thread, the random access thread slows down by 11x. So random access thread is more easily slowed down. So we're going to try to prioritize random access threads in this shuffling. So why are these threads different? Just one example. The random access thread, what it does is it actually spreads its requests, assuming it is of the same memory intensity with the streaming thread. It spreads its requests in these banks because it's random access, right? Whereas the streaming thread, basically it has high bank level parallelism. All requests are mostly parallel. Whereas the streaming thread, it keeps accessing the same bank over and over. So it has high robot for locality and probably low bank level parallelism because all requests go to the same row. When you run these two things together, streaming thread captures this bank and random access thread gets delayed in that bank. So it gets stuck over there. As a result, it gets high impact in terms of its performance. Its parallelism is destroyed in this case, right? If you look at this. If you did the prioritization in the other order, I don't have it over here, but random access thread would finish first and then the streaming thread can capture the bank.
There's no manufacturers that maps page is
Across the bank?
yeah.
So it depends on the manufacturer. Some of them are actually configurable. Some of them do cache block interleaving across the bank. Some of them do page interleaving. But if you do cache block interleaving, then a lot of the threads are random access, unless your stride is high.
Yeah, but
Mm-hmm.
you could imagine that you have, let's say, 4 or 8 cache blocks in one bank.
That's right. That's right. So you could actually reduce the effect of the streaming thread by actually doing interleaving at a sub-page granularity. And that makes sense, I think. We've looked at that a lot. And there's an IBM paper on that also, sub-row interleaving. I think that makes sense. So that reduces the effect of the streaming thread, but it doesn't fully get rid of it. Yeah. So basically, the random access thread is more vulnerable to interference, and it has high bank level parallelism. So basically, we have a metric called niceness. It's not the best metric in the world, but we try to quantify the difference between the threads. Niceness is high if you have high bank level parallelism. It's low if you have high robot for locality. That's the idea. Because high robot for locality causes interference, as we've seen. So we have a metric in the paper that's described. You basically compute the ranks of the threads based on these two metrics and subtract the rank of robot for locality from the bank level parallelism rank to get the niceness of the thread. A thread is nicer if it has high bank level parallelism. So how do you use that, basically? Let's take a look at the shuffling that happens. Remember, we're shuffling the ranks in the intensive cluster of the threads. If you do round-robin shuffling, let's say some threads are nice, some threads are not nice. If every thread gets equal priority in the shuffling, this is what would happen. In a shuffling, oh, I guess I don't have this animation nicely done. Basically, each thread becomes the highest priority during a shuffling interval, if you have enough shuffling intervals. If you look here, each thread is prioritized once. But if you look overall, the least nice thread causes a lot of interference over time. Basically, it's in front of many threads over the shuffling, over multiple shuffling intervals. And if you actually have more threads, this becomes bigger. So nice threads receive lots of interference. So we're going to prevent that with niceness-aware shuffling. And the basic idea is to keep the least nice threads or less nice threads at the bottom, such that they come to the top once in a while, actually once very infrequently, but they mostly stay at the bottom. So if you do this, for example, A stays at the bottom, but it props up to be the high priority only once across shuffling intervals. As a result, again, each thread is prioritized, the most prioritized once, and least nice thread stays mostly deprioritized. Okay. So that's the idea, basically. We do clustering to divide the threads, prioritize the non-intensive cluster over others, and employ different policies in each cluster. And the policies in intensive clusters are the most interesting for fairness and performance. So how does this operate? This is quantum-based operation. Basically, In a quantum, the memory controller monitors thread behavior. It looks at memory intensity, MPKI, bank level parallelism, row buffer locality. At the beginning of the quantum, of the next quantum, it performs clustering, the way I described earlier, and computes the niceness of intensive threads. And based on this, it forms a schedule over the shuffle interval. And that schedule can be relatively simple. You can basically fix a schedule at the beginning so that you don't need to compute the ranks every single shuffling interval because it's very fine-grained. So shuffle interval is very small. Quantum is much larger. And the scheduling algorithm after that is relatively simple. Basically, a rank is computed at the beginning over here for all shuffling intervals. And that's a permutation over here. Requests from higher rank threads are prioritized. And I already described that ranking mechanism. Row-hit requests are prioritized over others after this priority. And older requests are prioritized over others after that priority. So it's still a priority-based scheduling mechanism. You form a single priority level for each request. Okay? And this is the implementation cost. I guess this is assuming that you have thread IDs. If you already have thread IDs, the storage cost is not that bad. But that's Andrea was asking yesterday, what's the what is one of the hurdles of implementing? What are some of the hurdles of implementing these in machines? And some of the manufacturers have trouble even putting the thread IDs into the memory controller. But that has to be done to actually get some quality of service in the memory controller. So that's a necessary hurdle that needs to be overcome. Make sense? Okay. Okay, let's take a look at the performance of this. I'm not going to go over this previous work because I've already covered all of these schedulers. So where does thread cluster memory scheduling fall? I'll put these over here. But with the same workloads, this is where TCM falls. Basically, it's better in terms of performance than Atlas, and it's better in terms of fairness than PowerBS. So you could actually achieve toward that ideal better. And the hope is that there will be better scheduling mechanisms that push us toward that way. And I think this is another example of heterogeneity, where you can use heterogeneity to get the best of both worlds or approximate them. There's another interesting thing, which is the fairness throughput trade-off. These different algorithms have some configuration parameters. For example, FRF-CFS actually has a cap parameter that I discussed yesterday. This is present in AMD controllers, as far as I know. Basically, the idea is there's a cap on how many requests can be reordered over the oldest request. And if you vary that cap, you get this weird trade-off between fairness and throughput, at least for these workloads. So it's not very easy to understand. If you vary the unfairness threshold, tolerable unfairness threshold in STFM, you get this weird movement in space over here. If you vary the marking cap in PowerBS, you get this, again, weird movements in terms of maximum slowdown and throughput. In Atlas, you vary the quantum, you get this. If you vary the cluster threshold on TCM within reasonable bounds, this is the fairness throughput curve you get. So these are actually nice points. You might want to be in any point depending on whether you favor fairness or throughput. Okay. So it's more robust than other scheduling algorithms. So this is the OS can actually trade off between fairness and throughput if we can actually if we can know how to use this knob. And we have mechanisms to enforce thread weights also within each cluster, and these are in the paper. So to conclude, the previous scheduling algorithms that I described yesterday do not provide the best of both system throughput and fairness at the same time. We wanted to provide both of them at the same time, and we realized that a single policy for all threads is insufficient. Thread cluster memory scheduling groups threads into two clusters, prioritizes the non-intensive cluster for throughput, shuffles priorities in the intensive cluster for fairness, and shuffling favors nice threads for fairness purposes. And if you look at actually doing this shuffling in a niceness-aware manner, that improves fairness. That doesn't improve performance that much. That reduces the variance in slowdowns. And it provides the best system throughput and fairness for these workloads that we have studied. There are upsides and downsides to this also. The upside is, well, I've already told you that, right? It's reasonably simple to implement, but complex, more complex than Atlas, of course, right? That's I don't know which one is more complex, PAR-BS or TCM. Both, both are, I think, reasonably similar. There are downsides to this also. It doesn't scale to large buffer size. Actually, many of the scheduling algorithms that we've looked at don't scale to large buffer sizes. And this is the problem we're going to talk about very quickly. And it's not effective in a heterogeneous system. Heterogeneous meaning CPU and GPU. That was a very interesting direction to follow for us after this point. So we looked at that. And I'll briefly give the idea of staged memory scheduling, because I think going forward, this both simplifies the memory scheduler design, and it also makes it more scalable as well as application aware. I guess the problem is you need large request buffers as you scale up the system. And CPU, GPU systems is a place where you really need that large request buffer today. And the existing application-aware memory scheduler designs are hard to scale because they're monolithic. And they do consider a lot of properties when doing scheduling. The idea in staged memory scheduling is simple. It's basically to decompose the memory controller into 3 simple stages. One is batch formation to maintain row buffer locality. I'll not go into detail in any of these. I'll just give the high-level ideas. The second is to have the batch scheduler to reduce interference, doing application-aware memory scheduling. And the third is the DRAM command scheduler. These are basically FIFO queues to issue requests into DRAM. And I'll give a pictorial example of this. And compared to, if you actually do this, if you divide the scheduler into these 3 stages instead of having a monolithic scheduler, this is significantly more simple and more scalable and provides higher performance and fairness, at least in CPU, GPU systems. And I think you can modify this, the algorithms that we employ here, especially in the batch scheduler, to provide good performance and fairness in multi-core systems also. So the problem is this. Basically, you need large request buffers if you have a system like this, a bunch of cores and a GPU. And GPU is the purple one, as you might guess. It has lots of requests. It floods the request buffer. If you need to have a scheduler that looks at this request buffer, that scheduler needs to be big also. So we're going to replace that with 3 stages. The first stage is FIFO queues that actually take requests from different cores. And these FIFO queues form batches. If the requests arrive to the same row, you form a batch of requests. Basically, you merge those requests, and downstream, you send that larger packet that says, I have 3 requests to these row, and it goes to these parts of the row.
You have to be combined in the queues?
That's right. You combine a request to the same row in the queues, in the FIFO queues, not at the memory scheduler. And you could have these queues in the cores, actually. The second step is batch scheduler. The idea is basically to look at the queues and prioritize one of these queues for a given batch. And we have algorithms that actually trade off between, so there are 2 algorithms. One is shortest job first, and the other is round robin. Very similar to thread cluster memory scheduling. And we switch between round robin and shortest job first in a probabilistic manner, where the probability is actually determined by how much weight do you give to the GPU versus the CPU. You could actually extend this to different ways. This is not the best part of the mechanism yet. Yes?
For combining for reads, okay, for writes,
For writes, that's right. If you do the combining, if this is at within the memory controller, it's still okay.
for writes, you got a lot of complexity. Because you have not only to combine request and saying, oh, I would have to have this kind of line, this line, but you have also to associate with the data.
That's right. You still need to have the data.
Yeah, and combining them with the queue is not that easy.
Oh, I see. Sending. So what we do is basically we combine the request and send the data, pipeline the data. So we don't send all of the data. That's right. I see what you mean now. That's right. So the batch scheduler, I think, can employ different policies. What's done right now is to switch between shortest job first and round robin. Basically, you either select the round robin from the queues or the shortest job. shortest job meaning the least intensive thread. Okay. And once you do that, you select the batch to schedule, and that batch is entered to the different queue in the bank. And this is basically a FIFO that enforces the DRAM timing constraints. And for reads and writes, you switch modes as many memory controllers do today. So you can, but the data needs to be pipelined. So that's the basic idea. So this is a FIFO queue. This is a scheduler that looks at the batches and the characteristics of the applications. And these are FIFO queues also. Oh. I guess this is one animated example that shows that. So GPUs usually have large batches because they have good robo for locality. And some of these have good robo for locality. Some of these don't have good robo for locality. Basically, let's say your current batch scheduling policy is shortest job first. You pick the thread that is not intensive, and that gets scheduled to its bank. And then, let's say, probabilistically, the memory controller switches to the round-robin policy. And basically, it starts from round-robining between the cores. And it sends this batch. And later, a new batch gets formed over there. And there are a bunch of requirements for the batches. Because you may want to keep the requests over here to actually combine the requests to the same row. But you don't want to keep them for too long because that increases your latency. So if the memory controller is actually not congested, we don't form batches. They basically bypass the queues. Okay, and then round robin, basically you keep round robining between threads as long as the policy is round robin. So the complexity of this, with an RTL model, this actually consumes 66% less area than a row hit first scheduler that doesn't do any application-aware memory scheduling. And its static power is 46% less, and its dynamic power is similarly less. I don't have it up here. And the complexity reduction comes from, basically, we don't have a monolithic scheduler anymore. It's a stage of simpler schedulers. We actually do scheduling at each stage over there, right? Each stage is a simpler scheduler, considers fewer properties at a time. Each stage has simpler buffers. There are FIFO instead of out of order. Each stage has a portion of the total buffer size. The buffer is actually distributed across the stages. Any questions? Okay. So how does this perform? Very briefly, this is an area where I think if you don't understand the CPU metrics, we definitely don't understand the GPU metrics, CPU system metrics here for multi-program workloads. So what we did was basically we gave weights to GPU, and we varied that weight. And we have a system performance metric that takes into account the GPU weight. And this is the performance that you get with the best previous scheduler. And best previous scheduler actually depends. Atlas is the best previous scheduler if your GPU is not important. And this kind of makes sense because GPU is very memory intensive, right? TCM is the best scheduler if you have similarly important GPU and CPUs. And if the GPU is really important to you, it turns out the best previous scheduler is a row hit first scheduler because GPU applications have very good robo for locality. And losing that locality with any of the other schedulers is not a good idea. Because if you think about it, all of these application-aware schedulers actually lose robo for locality, right? Because they switch to some other application because the streaming applications are not usually fair. So SMS, stage memory scheduling, is much better than the best previous scheduler when GPU is less important. And it actually tracks first ready, first come, first serve. And it's slightly better than that when the GPU is important. So basically, at every GPU weight, SMS outperforms the best previous scheduling algorithm for that weight. Okay. I've gone very quickly, but if you're interested, you can read the paper and tell me why the metrics are terrible. And I agree. I don't think there's a very good way of doing this. And this is a very interesting area of research, I think. How do you actually quantify the performance here? As well as how do you scale the system? And going forward, I think probabilistic policies to manage these resources will become more important. Because probabilistic policies enable better scalability, I think. Okay. So far, we've been, I think, waving hands a little bit. Everything was best effort. So we wanted to provide stronger memory service guarantees as well. Basically, going forward, one of our goals is to satisfy performance bounds requirements in the presence of shared main memory, prefetchers, heterogeneous agents, and hybrid memory. This is a grand goal again, but we're going to start with a simple byte, hopefully. The approach is, if we can develop techniques or models to accurately estimate the performance of an application or agent, I call it. It could be something, some hardware agent, right? In the presence of resource sharing, we can develop mechanisms to enable the resource partitioning and prioritization mechanisms to achieve the required performance levels for all applications. So if we can estimate the performance with resource sharing, we can perhaps change the partitioning and prioritization to actually achieve the goal that we want to achieve. Of course, all the while providing high system performance, right? Otherwise, this is very easy to do. So I'll talk about one way of doing this when main memory system is shared between applications. And we're going to modify the memory scheduler, but we're going to drive it with a performance model this time. So the problem is unpredictable application slowdowns, and I've shown you this before. This is one example. Leslie is run with GCC. It slows down by almost 2x. If it's run with MCF, it slows down by almost 5.5x. So an application's performance depends on what it's running with. But we want predictable performance, and there are many reasons for this that I've discussed earlier. I'll briefly go over them quickly. Basically, in mobile systems, interactive applications can run with non-interactive applications. You need to guarantee the performance for interactive applications, right? In server systems, data centers, cloud systems, different users' jobs are consolidated to improve efficiency, all kinds of efficiency, power, area, cooling efficiency. And you need to provide bounded slowdowns to critical jobs at least to satisfy service level agreements. So our goal is to have predictable performance in the presence of memory interference. And we're not going to do very hard predictability. We're going to try, again, we're going to be soft. I think a very hard one is very tough. So the approach is we'd like to estimate the slowdown of each application and control that slowdown once we estimate it. So what is slowdown? I've already discussed this. It's the performance of an application alone divided by its performance when it's sharing resources with others. So the first observation is that if you have a memory-bound application, the performance of the application actually correlates with the memory request service rate. This is a result from a real system, Intel Core i7, with a memory bandwidth of 8.5 gigabytes per second. And this is the normalized request service rate an application gets. Normalized means one means it's getting the full bandwidth available. It's not using it, but it has it available for it. And this is normalized performance it gets. One means the performance it has when it has the full bandwidth available. So we vary this in a predict.
How do you measure that?
Oh, how do we change this?
Yeah.
So the way we change it is we have a hog application. Just 1 second. My PowerPoint has its own mind, so I'm going to change that. Not a good idea. So we write a micro benchmark that hogs part of the memory bandwidth, basically. So 50%, we write a micro benchmark that hogs 50% of the entire system's memory bandwidth, and run it with this application.
Yeah, but the 50% depends on who is running.
So we make unavailable 50% of the peak bandwidth. So one means this application has 8.5 gigabytes per second available. It may not be using it.
It runs
Yes.
alone.
That's right, it runs alone. 0.5 means it's running with this micro benchmark that's...
That use
Yes.
4 point out of the bandwidth when it is running alone, or when it is running.
When it's running together with this. Yes.
Okay.
Okay. So you get this linear curve for a memory-bound application. And this is true for many memory-bound applications. So the first observation is that you can actually change this equation to request service rate. Basically, you can approximate. You can use request service rate as a proxy for performance for memory-bound applications. So you could rewrite the slowdown equation as request service rate alone divided by request service rate shared. And the hope is that these are easier to estimate than slowdown itself. Well, this is definitely easy, right? You can estimate the request service rate an application is getting. Request service rate means how many requests per second are satisfied when it's sharing resources with others. But how do you get the request service rate alone of an application when it's running together with other applications? That's harder. And that's where key observation 2 helps. Basically, request service rate alone of an application can be estimated, approximated, by giving the application highest priority in accessing memory. So if the application is given the highest rank, highest priority, the hope is that it receives little interference from other applications. So it's almost as if the application is run alone. That's not exactly true, obviously. Let's take a look at why this is the case. Let's say this is the example where the application is running alone. It has 2 requests, and it has 2 time units to service those requests. When it's run with another application, let's say this is the scheduling that happens with some priority. The application that we're concerned with receives interference, so it has 3 time units. It takes 3 time units to service its requests. Whereas if we prioritize this red application, what happens is the memory controller would delay this blue request from another application, and the red application's performance will be the same as, hopefully, as if it's running alone. That's right. No, you cannot. You cannot say, I want to prioritize this application today. So you still need to change the memory controller here. And we're going to change it a lot, actually. So, okay. This was the, basically, once you realize this, the mice model, memory interference induced slowdown estimation model for memory bound applications becomes this. Request service rate alone divided by request service rate shared. And we can estimate both of these. This is for a memory bound application, and it works for a memory bound application because memory bound application looks like this, right? It is dominated by the memory phases. It has little compute phase, and it has a large memory phase, and as a result, because memory phase slowdown dominates overall slowdown when it receives interference, you can approximate the performance of the application with the request service rate. But if you have a non-memory bound application, it looks the exact opposite, right? You have compute phases dominating the memory phase. And if you look at request service rate, that actually approximate the performance of the memory over here. So if your initial memory phase is alpha fraction of the time, and your non-memory phase is 1 minus alpha fraction, this 1 minus alpha remains approximately the same with interference. It's not perfect again, but it remains approximately the same. But this alpha is actually scaled. And it's scaled by this increase slowdown in terms of the request service rate, alone divided by request service rate shared. So basically, only memory fraction slows down with interference for non-memory bound applications. As a result, we change the model to be this way. Basically, the slowdown of a non-memory bound application is 1 minus alpha, which is the compute phase, compute fraction, plus alpha times the slowdown in terms of request service rate. Because that's the only part that slows down. Again, this is approximate. Okay, so how do you measure request service rate shared in alpha? Basically, request service rate shared, we have a per core counter to track the number of requests serviced. And at the end of each interval, we measure number of requests serviced divided by interval length. So this is easy, actually. Alpha is relatively easy also. We count the number of stall cycles at the core and compute the fraction of stall cycles for memory. This is the harder part, request service rate alone. Because the application is running together with other applications, right? It's not running alone. So the idea is to periodically give each application highest priority in accessing memory to estimate this. Basically, we divide the each interval into shorter epochs. At the beginning of each epoch, the memory controller randomly picks an application as the highest priority application. And at the end of an interval, for each application, it estimates this. Number of requests during that high priority epoch divided by number of cycles the application is given high priority. Basically, how many requests did you get serviced during the time you were given high priority? That's the idea. Now, if you do this enough times, hopefully you'll get enough samples to figure out the request service rate of an application. And we're going to try to do it enough times. So there's a downside, of course. This is not that simple, it turns out. There's still interference that happens even if you give high priority to an application. So basically, that's the problem we're going to fix. There is an inaccuracy in estimating request service rate alone. We're not going to fix all of the inaccuracies. One inaccuracy is the row buffer locality changes, for example. You can fix that with shadow row buffers, and that improves accuracy, but we're not going to do that for these results. But another inaccuracy happens because the memory scheduling is not preemptive. So what happens is, let's say this application is given high priority, and another application sends a request, and while this request is being serviced, this red application sends another request. Because memory scheduling is not preemptive, the memory controller first finishes this blue request and then services this red request. Right? As a result, what happened is this high priority application did not really get high priority. Right? Because this blue application sneaked in one request and the memory controller serviced it because of its non-preemptive scheduling. So you have interference cycles because of this. And this turns out, it turns out that this happens quite often. So we want to take that into account. One solution is to determine and remove these interference cycles from this RSR alone, request service rate alone calculation. Basically, the idea is the memory controller, whenever this interference cycles happens, the memory controller can detect that, right? If the highest priority application has a request, but the bank is servicing another application's request, you basically have a counter. It's not perfect again. But basically, this is what we're going to do. We change the request service rate alone equation to number of requests during high priority epochs divided by number of cycles applications given high priority minus the interference cycles. Basically, we're not going to count those cycles where the application is delayed because of some other application as the high priority cycles. Okay. I think we've already talked about that. Okay. So that's the model, basically. That's the performance estimation model. If we put it all together, given an epoch or interval, the memory controller measures request service rate shared and alpha and estimates request service rate alone. At the end, it estimates the slowdown of all applications. And the next interval, it basically does the same thing. We're going to do something else over here for the memory scheduling. But let's take a look at how good this model is. We've already looked at actually some slowdown estimation model, which was stall time fair memory scheduling. Fairness via source throttling, which we briefly discussed yesterday, which I will talk very, very briefly today also, uses a similar model to stall time fair memory scheduling for main memory slowdown estimation. And there's some recent work from University of Ghent that actually does something similar to this for main memory purposes. So the basic idea of stall time fair memory scheduling was to actually try to compute the stall time alone, estimate the stall time alone, and estimate the stall time shared, and divide those two. And this was easy again, but this was very hard, right? And it's still very hard because we tried to count the number of cycles an application receives interference. So the key advantage of mice over STFM is STFM, stall time fair memory scheduling, tries to estimate alone performance while an application is receiving interference, while it's not the highest priority application. And this is hard. You have to really, to do this really perfectly, you need to emulate the memory controller. And memory controller is already complex to design. Whereas mice estimates alone performance while giving the application the highest priority. This is easier. Again, it's not perfect, but it's better, as I'll show you. The second advantage is STFM doesn't take into account the compute phase for non-memory bound applications. So if an application is not stalling for memory, STFM doesn't know what fraction of that is. So mice accounts for the compute phase, just like we discussed, so it has better accuracy. So let's take a look at what that accuracy is like. We have a detailed DRAM model and a bunch of workloads. We formed 300 multi-program workloads with Spec CPU 2006. I'll show you one example. This is Leslie 3D. When it's run with 3 other applications on a 4-core system, this is the actual slowdown measured in the simulator over some number of cycles. And I don't know why that disappeared. That's interesting. OK, it came back. There's a glitch somewhere in PowerPoint, I bet. That happens a lot, actually. So this is the actual slowdown that you see. And this is the slowdown estimation with stall time fair memory scheduling, which is not very accurate. And this is the slowdown estimation with mice. So mice keeps track of the slowdown reasonably accurately. And you can do better if you make the model a little bit more complex, actually, but we don't want to make it more complex than it is. And these are more results. The top part is the memory-intensive applications. And these are the actual slowdowns. These are the slowdown estimations with stall time fair memory scheduling. And stall time fair memory scheduling doesn't do too well with the memory non-intensive applications because it doesn't take into account the compute phase. And these are the slowdown estimations with mice. So mice usually keeps track of the slowdown better. And if the application doesn't slow down, mice doesn't think that it's slowed down because it does take into account this compute phase. So the average error in terms of slowdown estimation is 8.2% across 300 workloads, whereas the average error of STFM is about 30%. So now that we have the slowdown estimation model, let's try to provide soft slowdown guarantees. And I'm going to say soft because there's going to be no guarantee at all, actually, in the end. It's all going to be empirical and probabilistic. So the goal is to ensure quality of service critical applications meet a prescribed slowdown bound, at least most of the time, and maximize system performance for all other applications. The basic idea is to allocate just enough bandwidth to quality of service critical applications and assign remaining bandwidth to other applications. So how are we going to do that? Basically, we have an initial bandwidth allocation to the quality of service critical application, and we're going to estimate the slowdown of that application using the mice model. And after every n intervals, if the slowdown is greater than this bound, plus or minus some hysteresis, we're going to increase the bandwidth allocation. And if the slowdown is less than the bound, then we're going to decrease the bandwidth allocation for that application. And you can actually use different mechanisms for bandwidth allocation. Pair queuing, for example, is one example, or ranking. For example, you could give the highest rank to an application. If you give it the highest rank for every interval, you can assume that it gets 100% of the bandwidth. Again, it's not perfect, but that's what we will do. We're going to change what fraction of the time it becomes the highest priority application to give the bandwidth allocation. So when slowdown bound is not met for n intervals using this, we can notify the OS so that it can migrate or deschedule the jobs. So at that point, the memory controller can give up. I'm not beating the slowdown bound, at least with this. So let's take a look at the results. We have each application considered as the quality of service critical application, and we have 25 applications from the Spec 2006 suite. We run it with 12 sets of fixed co-runners of different memory intensities. So we have a total of 300 multi-program workloads. And each workload will be run with 10 slowdown bound values. So quality of service critical application will have 10 different slowdown bounds. We're not going to be able to meet all that slowdown bound every time. So the baseline memory scheduling mechanism we're going to compare to is a mechanism that basically always prioritizes the quality of service critical application. This is the best you can do, I think, without descheduling jobs or without doing source throttling. And other applications requests are scheduled in first ready, first come, first serve order. Let's take a look at one workload. We have these 4 workloads, and the quality of service critical application is Leslie 3D, and these are non-quality of service critical. If you always prioritize Leslie 3D, this is the slowdown you get, a little bit less than 2. And this is the best we're going to be able to achieve. If you use mice and the QoS mechanism that I described, if you set the slowdown bound to 10, this is the slowdown we get. So it's less than 3, and you get better performance on these other applications. If you set the slowdown bound to 3.33, you still meet the slowdown bound. The slowdown is less than 3.33, and the performance is better for these other applications. If you set the slowdown bound to 2, we almost meet the slowdown bound. It's 2 point something. And the performance is still better for these non-quality of service critical applications. And after that, we don't meet the slowdown bound. And it turns out performance is still slightly better. But that doesn't matter, maybe, if you care about that slowdown bound a lot. Okay. So basically, we found that mice is effective in meeting the slowdown bound for the quality of service critical application when the slowdown bound is meetable, just with memory scheduling, and improving performance of non-quality of service critical applications. So we've actually expanded this. We look at 3,000 data points, and you can actually classify whether we can meet the slowdown bound or not meet the slowdown bound. And the orthogonal axis, can we actually predict that we meet the slowdown bound or not meet the slowdown bound? Prediction means if you don't meet the slowdown bound for n intervals, then the memory scheduler says, I haven't met the slowdown bound. That's the idea. So for 80.9% of the workloads, the slowdown bound is met. And this actually good compared to always prioritize, right? Always prioritize actually meets the slowdown bound for 83% of the workloads. So we meet the slowdown bound when the slowdown bound is meetable just with memory scheduling, most of the time. And mice correctly predicts whether or not the slowdown bound is met for 95.7% of the workloads. So we can actually tell with 95.7% accuracy that the slowdown bound is met or not. Whereas there's no previous mechanism that can tell this. You could use STFM, but that has terrible accuracy in terms of that. I don't remember the numbers, but it's much less than 95.7%. Okay. I think I'll skip this. Basically, you get higher performance when the bound is loose, as expected, right? That makes sense. There are a bunch of other results in the paper if you're interested in that. Basically, there are a bunch of parameters in the model. Okay, I'll keep going. Actually, STFM is a comparison point too, but I didn't talk about it. But it doesn't do too well in meeting the slowdown bounds. And once you have the slowdown estimation model, I think you can use this for other purposes. And the paper talks about how to actually minimize the maximum slowdown with this. Any questions?
Who's going to set
Yes.
the slowdown bound?
Yes, that's a good question. So we don't deal with that issue in the paper at all. So hopefully the user or the operating system. Yes.
How the operating system can know the values which is possible to reach?
So it doesn't need to know. So the user can say, this is a slowdown bound, and the memory controller, if it doesn't satisfy it, notifies the operating system saying that I cannot satisfy it. And the operating system may then deschedule some jobs to actually try to satisfy it. Right? So it's going to be a feedback control loop, I think.
The operating system can consider that there are some jobs that are really try to reach some.
Yeah.
And what if you have several jobs that want to have
Slowdown bound.
a performance guarantee?
That's right. So we've looked at that case. We haven't extensively explored it, and this can help that case also. But it depends on the slowdown. If the slowdown bounds are very low, you may not be able to satisfy all of those slowdown bounds. So this, I envision this as part of a system that actually tries to provide quality of service overall. So hopefully the operating system does things to collect information over time and tries to put those jobs that go nicely with each other such that their slowdown bounds are satisfied. So this is, I think, support for the operating system such that it can do better in trying to satisfy all of those. And everything is best, again, everything is best effort, although a little bit stronger than the previous works. Yes?
How do your mechanisms behave when all the applications have a similar behavior? Let's say you run just a plain spec rate scenario. 8 cores all running the same application from spec. So how do these behave? I mean, do they give equal priority to all applications? Are they equally bad?
This last one, mice, or everything else?
The gamut of...
Okay, so all of these other ones actually, they're equally fair. So we maintain the fairness and actually improve performance compared to the baseline scheduling policies. The reason performance improvement comes is because we preserve bank level parallelism in all the mechanisms because of the ranking. And fairness is not changed because you actually shuffle the thread rankings for TCM, for example. For Atlas, if everything is similar, Atlas again balances the attained service over time. So if all applications are similar, there's no problem. Okay, to summarize, basically uncontrolled memory interference slows down applications unpredictably. Our goal was to estimate and control the slowdowns. The key contribution in this work is an accurate slowdown estimation model that has an average error of 8.2% versus approximately 29% in previous work. And the key idea is request service rate can be used as a proxy for performance And request service rate alone can be estimated by giving an application highest priority in accessing memory. That way you can estimate the slowdown of an application by using these parameters. And we can leverage the slowdown estimate to control the slowdowns. And we've looked at designing a memory scheduling algorithm to provide soft slowdown guarantees. And we've also looked at minimizing maximum slowdown. The results are in the paper. This does improve fairness. You could actually use this to design other memory scheduling policies or something else. Maybe you expose these slowdowns to the operating system and it does something else with them. Okay. Okay. I'll skip this because I gave you the key idea. But basically, going forward, I think providing even stronger guarantees is interesting. But also doing that for parallel applications is an interesting problem. And we've looked at parallel applications, and I've already given you the key idea. Basically, if you can estimate the limiter threads using mechanisms similar to bottleneck identification and scheduling, you can prioritize them. And for every other thread, you have a memory scheduler that shuffles the priorities such that everybody makes reasonable progress such that they don't become limiters. And if you do this, you get actually good performance. And this makes sense, right? One aside, I think, I wanted to add these slides because there's a lot of complexity in the memory scheduler, I think. And there's an interesting direction. At some point, it'll become maybe humanly impossible to think about these designs. Although I'm hoping that it's not going to be the case. It becomes, right? Because there's so many constraints. And actually, I haven't dealt with many other constraints, right? For example, I didn't talk about writes, prefetches, refresh. And if you consider all of them at the same time and other timing parameters, these are a mess to design. But basically, why are these difficult to design? First, you need to obey many DRAM timing constraints. There are many, like 50+ timing constraints in DRAM. For example, write-to-read penalty. This is the minimum number of cycles to wait before issuing a read command after you issue a write command to any bank. Row cycle latency, we've discussed this, right? Row cycling latency. And there are a bunch of other ones. So you need to obey these for correctness. You need to keep track of many resources to prevent conflicts, right? Again, for correctness. Channels, banks, ranks, data bus, address bus, row buffers. If you have subarray level parallelism, subarrays, we're increasing complexity. If you have tiered latency DRAM, tiers. Need to handle DRAM refresh at the same time, again, for correctness. There's slack in the refresh also. You have some elasticity in refresh. So if you want to improve performance, you take into account that one also. You need to optimize for performance at the same time. And all of these different optimizations that I've discussed require optimizations for performance in the presence of constraints. And reordering is not simple, as we've discussed, right? Especially if you have large request buffers. And we want to predict the future. You need to handle the row buffers. We were discussing that yesterday. How do you manage the row buffer? Do you use an open row policy or a closed row policy? Well, some memory controllers do prediction today. But that adds complexity also. And these are some timing constraints you can look up. And if you actually want to have a good understanding of the behavior of how DRAM works and what these timing constraints are, I would recommend these two papers that we've published. If you look at the data sheets, they're very hard to understand, I think. Yeah. But I'm hoping these papers are a lot easier to understand, and they tell you why these timing constraints actually exist. Not all of them, of course, not all of them. But basically, there are so many timing constraints. So what we wanted to do was to offload this human designer's job to a machine learning algorithm. And that's the idea of self-optimizing DRAM controllers. I won't go into detail, but I think going forward in designing complex systems using machine learning is an interesting solution. The downside, of course, is it's a black box, right? But the basic idea is because DRAM controllers are difficult to design, it's difficult for human designers to find a policy that can adapt itself very well to different workloads and different system conditions in the presence of all of these different constraints. Right? So our idea was to design a memory controller that adapts its scheduling policy decisions to workload behavior and system conditions using machine learning. And the observation is that I think DRAM control maps nicely, or reinforcement learning maps nicely to memory control. And I'll briefly talk about reinforcement learning, but I won't do justice to it because I have other things to discuss also. But the basic idea is to design a memory controller as a reinforcement learning agent that dynamically and continuously learns and employs the best scheduling policy. So the idea looks like this. Reinforcement learning, basically the idea in reinforcement learning is you have a learner or agent that basically observes the state of the environment. So you have some state space parameters, and takes an action based on that state. So it associates states to actions. And after that, it gets a reward based on that action. And that reward is immediate, but you can actually take into account the long-term effect of that state-action pair on the reward that you get. So basically, over time, you try to pick the best action given a state that can maximize the reward. And there are many different types of reinforcement learning policies. But basically, the way most of them work is you have state-action pairs and a reward value associated with it. And given a state, you find the reward value, you find the state action, you find the action that maximizes the reward that you would get in some long term. And actually, for this to work well, you need a Markov decision process. Basically, you need to be able to model the agent as a Markov decision process. And memory scheduler is actually nicely fits into this. Because, well, nicely fits into this if you're trying to optimize for one parameter. That's database utilization. So if you have, basically the scheduler can be thought of as looking at the system state attributes in the memory transaction buffer, or maybe some other state attributes that you give it. And the action is the command that it schedules next. And the reward it gets is the data bus utilization after some time, right? And you can do this, basically you have a scheduler that has a table that maps the states to actions, and each state action pair has a reward value that's updated over time. And whenever the scheduler needs to schedule a command, it looks at its state and looks at the possible actions, and it picks the action that maximizes the data bus utilization over time. And that's the idea. You can look at the paper for details, there are many reinforcement learning mechanisms, and people have actually implemented these in hardware a long time ago. And I believe they're going to be increasingly possible. The problem, of course, here is if you want to optimize for something else, you need to find that something else that nicely fits this reinforcement learning paradigm. And that turns out to be hard, I believe. Like if you want to optimize for fairness, for example, how do you map a scheduled command to the fairness decision, fairness that happens in the long term? That becomes hard. Data bus utilization is not that hard. Because you schedule a command and you know if the data bus is utilized or not utilized, right? And in the long term, you can accumulate that utilization. So that's the idea here. I'm not going into detail, but if you do this for these parallel applications, you can actually do much, much better than a row hit first scheduling policy. So this is the row hit first scheduling policy over here, FRF-CFS. And these are parallel applications from different workloads. And we get approximately 20% better performance, better execution time with these applications with a reinforcement learning scheduler. And we're actually increasing the data bus utilization. So row hit first scheduling policy is reasonably good for increasing data bus utilization, but we can do much better. And this is the best you can do. This is where the data bus is the limit. You remove all the timing constraints. And the ideal is actually 70%. Okay, for these workloads. I think going forward, somehow adapting this to other metrics would be very interesting. I don't know how to do that.
But I don't really understand your black box.
I don't either. So what it does underneath, I don't think I understand it. So we've tried to look at different policies, different orderings. So we basically have a feature selection. We've considered like hundreds of state attributes. A state attribute could be, is this request at the head of the reorder buffer, for example? How many writes do you have in your transaction queue? How many reads do you have at this point in your transaction queue? How many applications requests do you have? So we ran offline a feature selection algorithm that selected some features. And we use those features, combinations of those features to prioritize, and we still don't get the performance benefit that we get with this reinforcement learning controller, because reinforcement learning actually adapts dynamically these values. And we cannot, the policy changes over time. So we do not know what the policy is. We can potentially analyze at a given instant, but we may not be able to make sense out of it. That's always the problem with machine learning techniques, right? It's a black box. And that's the biggest downside for adoption too, probably, right? Because if the designer doesn't understand the technique, will they actually be willing to implement it?
Yeah.
Unlikely unless you're doing data analytics and so I think it's an interesting approach. Okay, let's see. We still have time. Let's take a look at very briefly the dumb resources approach. I will talk about the smart resources, but there's another approach to providing quality of service, and I'll go very quickly over this. And I briefly talked about the source throttling. Basically, the idea here is to keep each resource free for all, not change the memory scheduler, keep it FRF-CFS or machine learning-based memory controller maybe, but control injection into the system somehow such that unfairness doesn't happen or such that you improve performance. And I'll briefly discuss fairness via source throttling. The motivation here is you have many different shared resources: cache, memory controller, banks, interconnect. If you want to design each of these with a different interference control mechanism, first of all, you need to find a good interference control mechanism. You need to find a good memory controller, quality of service over memory controller, good quality of service over interconnect, good quality of service over cache. And we've seen that we haven't still designed the best quality of service over memory controller yet. And once you do that, you may need to coordinate the actions that each of them take, right? Because their actions are actually uncoordinated. And we've seen that with our results. And that coordination may require complex implementation. Other people have proposed machine learning techniques for this purpose. So the question that we asked was, how do we enable fair sharing of the entire memory system by controlling interference in a coordinated manner without requiring many changes to these resources? And the alternative approach is source throttling. And the idea is to manage inter-thread interference at the cores themselves, not at the shared resources. Basically, if we can somehow insert enough counters to the shared resources such that we can dynamically estimate unfairness in the memory system, and we could potentially do that with mice model, for example, we could feed back this information into a controller, and the controller throttles cores' memory access rates accordingly. And whom to throttle and by how much depends on the performance target. Again, you could configure this. For example, if unfairness, for some definition of unfairness, is greater than system software specified target, then the the controller can throttle down the core that's causing the unfairness and throttle up the core that was unfairly treated. And this is described in this paper. I'll not go into details of how it's done, but hopefully there's a good idea of how we can estimate unfairness. But basically, during an interval, the slowdown in the system is estimated for different applications. And this mechanism, runtime unfairness evaluation mechanism, estimates the system unfairness, finds the application with the highest slowdown, or applications with the highest slowdown. In this mechanism, we have one application. Finds the application that's causing the most interference for the application with the highest slowdown. And at the end of the interval, these estimates are provided to the dynamic request throttling engine. Basically, the dynamic request throttling engine checks the unfairness estimate. If the unfairness estimate is greater than some target that's provided by the system software, then it throttles down the application that's interfering with the application that's slowest by limiting its injection rate and memory level parallelism. You could do this with DVFS, dynamic voltage and frequency scaling techniques today, but that also reduces the compute speed of an application. So we actually have mechanisms to limit the injection rate. And throttles up the application that's been slowed down the most, treated most unfairly. So this is the mechanism that we evaluated. But of course, it's a configurable mechanism. So you can actually have different fairness objectives configured by system software. For example, you can keep the maximum slowdown in check. You can trigger this dynamic request throttling if the maximum slowdown is beyond some threshold value. Or you can keep the slowdown of a particular application in check. You can trigger that dynamic request throttling if an application's slowdown target is not being satisfied. And you can estimate the slowdown of an application using something similar to what I've discussed earlier. And you can have support for thread priorities. You can basically weight the slowdown with the weight of the application. So I'll not show you any graphs, but I'll give you some takeaways. Basically, if you do the source throttling alone, just for fairness purposes, it provides better performance than a combination of smart memory scheduling and fair caching. Now, take these results with a grain of salt because we didn't employ the best fair caching and best memory scheduling algorithms. But basically, we found that decisions made at the memory scheduler and the cache sometimes contradict each other, even if you design these to be quality of service aware. because you don't coordinate. Because if you give more cache to an application, that may reduce the cache for some other application, but that application may be interacting badly with the applications underneath in the memory controller, right? Maybe it has very bad robot for locality at the bottom. But we also found that neither source throttling alone nor smart resources or smart memory controller plus smart cache alone provides the best performance. So the best approaches are actually combined approaches. If you actually combine smart resources and source throttling, you get better performance improvements, as well as fairness enforcement. I ran through that very quickly. But there are other ways of doing this. I'll briefly talk about this. We've discussed this yesterday briefly. But you can actually partition the channels between different applications. And that's the idea here. Basically, system software somehow figures out badly interfering applications and maps their pages to different channels. And this is a cooked up example. Let's say you have 2 channels, 2 applications. Nice, right? It doesn't always work that way. But just for illustration purposes, you have application A, application B. With conventional page mapping, pages may be mapped such that this application, both applications access both channels. And as a result, they interfere with each other. Whereas if you map these applications to different channels, what might happen is both applications' performance improves because both have reduced interference. Well, life is not this nice. You don't have as many channels as applications. And this application may need more channels also, right? Because if you partition the channels, you're reducing the parallelism an application gets. So how do you actually do this channel partitioning? We have mechanisms to do this. Basically, the idea is to separate badly interfering applications as much as possible. And what are badly interfering applications? If an application has low intensity and another application has high intensity, you'd like to separate them, assuming a row hit first memory scheduler. If an application has high robot for locality and another application has low robot for locality, you'd like to separate them with a row hit first memory scheduler. And that's the idea. And if you do this, you can this is especially effective in reducing interference of threads with medium and high intensity, it turns out. Because those are the applications that destroy each other a lot. And we found significant performance improvement over existing systems. So how does this work? Very briefly, the hardware profiles the applications, figures out the robot for locality and miss rates, and classifies applications into groups. And groups are basically, I'll show you that grouping. It partitions channels between application groups, and this is soft partitioning. And it assigns a preferred channel to each application. And the system software allocate application pages to the preferred channel. And this happens over intervals, so it's dynamic. We looked at dynamic migration of pages also when the application changes behavior. There is overhead associated with that, so you need to overcome that overhead. We found benefit from that, but that overhead can be very high. So this is the hardware's job. This is the system software's job. And this happens over an interval, right? At the end of an interval, you do this. So how do you classify applications? Basically, we collect misses per 1,000 instruction for an application. If it's low, the application is low intensity. If it's high, the application is high intensity. And for high intensity applications, we look at their locality also. For low intensity applications, locality doesn't matter as much. But for high intensity applications, you don't want 2 high intensity applications that have very different localities, robot for localities, to be mapped to the same channel. Okay. And yes?
This leads to put low intensity applications in the same channel and high intensity applications on the other channels. You got it to
That's right.
got
Imbalance.
one channel that does much more.
That's right.
pressure.
That's right. And that's one of the downsides of the approach. If you're, so what we do in the end is to find those applications that are low intensity, that do not consume a lot of memory bandwidth, and prioritize in the memory scheduler. That way those applications are mapped anywhere, and applications that are higher intensities are partitioned across the channels. So that alleviates that a little bit, but that doesn't get away from that totally. So we do introduce load imbalance, and that improves performance. But if you do not do it very well, it's not very robust. I agree. Okay. think I'll summarize the memory QoS and then I'll talk about two caching ideas. Is that good? Unless everybody's tired and it's actually warm here.
The last time, so
Okay. Okay. All right. So we've talked about memory QoS a little bit, but actually we've talked about a lot of things related to the memory system. When I first started, I guess this was the second lecture, we talked about some technology, application, and architecture trends that dictate new needs from the memory system. And these three major needs are scalability, like how do you scale DRAM, given the DRAM scaling problem. We talked about DRAM system co-design. We didn't talk about new technologies that much, but that's also interesting, I think. The second one was quality of service, and we've mainly talked about quality of service in this lecture. And the third one is efficiency, customizability, providing minimal waste, and how to use new technologies to provide energy efficiency. We've kind of touched into customizability, configurability, with respect to quality of service. So that was the focus in the last two lectures, 1.5 lectures. If you have the conclusion is that if you have quality of service unaware memory, it's uncontrollable and unpredictable. Providing quality of service awareness improves many things: performance, predictability, fairness, and utilization of the memory system, as well as utilization of the cores. And we've looked at several approaches and several techniques. There are two approaches overall: designing the resources to be smart, or keeping them dumb but doing something else at the periphery. And both approaches are actually effective in reducing interference, but there is no single best approach for all workloads, what we found. You would like to really combine these approaches if you want to design a perfect system. And there are three techniques that we've discussed. I think these are fundamental to many different quality of service mechanisms. One is request scheduling or thread scheduling, which is similar, which we did not discuss. Source throttling and memory partitioning, which is channel partitioning. All approaches are actually effective in reducing interference, and they can actually be applied at different levels, hardware versus software. But there's no single best technique for all workloads, so we would like to combine them again. And one example combination of approaches which we just discussed is integrated memory channel partitioning and scheduling. Actually find out the applications that you would like to prioritize in the scheduler and prioritize them, and partition the memory channels across higher